Hi everyone, my name is Yaoyiran Li, and today I will be presenting our work on two-headed monster and crossed co-attention networks. This is a joint work with Jing Jiang. Our work is totally on a novel co-attentional mechanism. We all know that co-attention is widely adopted in multi-modal scenarios. In this work, we emphasize a parallel and symmetric manifold operating on two input channels and possessing two output channels, but do not assume that the two channels of input must be different or multimodal. We first formulate the co-attention mechanism in a generic way, and then we propose a paradigm called two-headed monster, which consists of two symmetric encoder modules and one decoder module connected with co-attention. As a specific and concrete implementation of two-headed monster, crossed co-attention networks are designed based on the transformer model. We test crossed co-attention networks on machine translation tasks and show both advantages and disadvantages of the proposed method. Previous work defines a non-local operation based on self-attention in transformers. As shown in the formulae, the K, Q, and V features correspond to K, Q, V gates in the multi-head attention transformer. And in fact, the non-local operation degrades to the multi-head attention in transform. When we select proper F and G functions, we follow this style and provide a definition on generic co-attention. Our co-attention features two input channels, the left and the right. Accordingly, it has two parallel attention modules, each having three input gates, V, K, Q. The input feature map to each input gate, it is the V, K, Q gates can either come from the left channel or from the right channel, though there are possibly different ways of V, K, Q connections. This work as a preliminary investigation only show experimental results on the case that we will specify in the next slides, but leaves the study of how different ways of connections cater to different tasks as our future work. Once we have a definition on co-attention, we can introduce our two-headed monster paradigm. We expect this type of neural structures to benefit from having two parallel input channels that would be intertwined with each other through co-attention mechanism. As shown in the figure, the neural structure has two encoders and one decoder. Co-attention mechanism is used to not only connect two encoders, but also connect encoders with a decoder. Under the umbrella of two-headed monster, we design transformer-style networks termed crossed co-attention networks. In our encoder, the left attention modules takes V and K input features from the left channel and take Q input features from the right channel. The attention modules on the right branch, however, take V, K input from the right channel and take Q input from the left channel. In the encoder-decoder co-attention layers, the multi-head attention on two decoder branches uses the output from two encoder branches as V and K alternatively, while taking in the output of the self-attention layer in the decoder as Q. As mentioned before, we test our model on machine translation tasks. So we feed the same input sequence to left and right input channels in the encoder, but in order to reduce the redundancy of two parallel branches, we apply dropout and input corruption on input embeddings for two branches respectively. In particular, we randomly swap two subword tokens in the input matrices at a probability of 0.5. We demonstrate our model on WMT English to German and the WMT English to Finnish machine translation tasks. Our models are established with 6 encoder and decoder blocks and a hidden state of size 512 for base models and a hidden state of size 1024 for big models. Our experiments demonstrate the efficiency of our proposed crossed co-attention mechanism, which significantly improves the BLEU scores of machine translation compared to a standard transformer baseline, as illustrated in the table above. However, since the number of parameters roughly doubles, the epoch time also increases by roughly 60% to 80%. In addition, we also find that our models demonstrate a better capability of model selection. For example, as shown in the table below, our proposed method shows that in 25% of cases across all of our experiments, the model selected on the def set is also the best model on the test set. However, the baseline method does not show the capability. To conclude, first we formulate the generic co-attention. Then we propose two-headed monster neural structures consisting of two parallel encoders and a decoder connected with each other using co-attention. Then we design cross co-attention networks based on our defined co-attention under the umbrella of two-headed monster. Our proposed method improves the machine translation tasks by 0.17 to 0.74 BLEU points and enhance the capability of model selection. However, the time efficiency is reduced since the number of parameters increases. Our future work will focus on two aspects. First, we will adopt input from two different domains and test our model on tasks such as multimodal machine translation. We will investigate how different ways of co-attention connections will influence the model performance on different tasks. Okay, that's all I have for you today. Please send me an email if you have any questions. Thank you for your listening.